for this lecture and tomorrow's lecture, we will just be talking about one paper. I am just writing down the name of the paper. I think this is soda 14. Either 14 or 13, I forgot. Okay. So, everybody is here? Okay. Yeah. So, we are just waiting for you. So, I just thought I will just write down the name of the paper. Okay. So, let us start. Okay, it is 13. Yes, that I was confused. It does not say in the paper. Okay. So, let us start. As I said, for today's lecture and tomorrow's lecture, we will be just discussing this paper, and as the title suggests, it gives polylogarithmic worst case update time for dynamic connectivity. So far, the algorithms that we discussed, they were giving polylogarithmic amortized update time. This gives worst case update time, and this was a big open problem in this area for several years, and actually this paper got the best paper award in SODA 13. So, this is a pretty big result. So, before we proceed, how many of you are familiar with randomized algorithms, say Chernoff bounds and so on? Okay. So, nevertheless, for the sake of completeness, then let me just spend the first 10 minutes just describing some basic results from concentration bounds. So, sorry, yes, it is going to be a randomized algorithm. Okay. I am just going to state the result, but what does this result say, Chernoff bound? Okay. Suppose you have one coin and you toss it, the outcome can be, suppose it is a fair coin, right, the outcome can be either head or tail. Now, you can see that in some sense the outcome is very uncertain, you do not know whether it will be head and tail, it has equal probability. Now, suppose I tell you that you toss 1000 or say 10,000 such coins, and will the number of heads that come up be close to say 5,000? What do you expect? You expect that it will be close to 5,000, right? And you intuitively you feel that it is very certain that they will be close to 5,000, because you are tossing so many of them. And Chernoff bound basically just quantifies this idea that whenever you have many independent random variables and you are just running the random experiments over those random variables, when the expectation is large, the total sum, the outcome will be very concentrated around its expectation. Okay. And now I am just going to state the formal result. So, suppose there are much general versions of this bound. I am just going to state the one that we might need. So, these are 0 1 independent random variables, dependent random variables, and x is their sum. Okay. I equals 1 to t x I, and now delta is some parameter. This is the error parameter, and now suppose you are just asking what is the probability that this sum x, let me first also write it down, mu is the expected value of the sum. Okay. And now suppose you are asking what is the probability that this actual value that this x takes is slightly larger than the expectation, and the bound is this. Okay. Now, what does this tell you? Forget about this delta square over 3, this factor for the time being. I myself do not remember this factor, but the story is this: as mu, the expectation increases, the probability of this bad event happening decreases exponentially in mu. That is the story. So, delta is some small constant, forget about delta. Okay. This is just some constant times mu. Okay. And this is the quantification that I was talking about. If you are just tossing one fair coin, this mu, what is this mu? Mu is half, right, that it comes up heads. So, mu is small, and hence you are not sure whether the good event will occur, whether head will occur or tail will occur, because this thing is small. But if you are tossing 10,000 or 20,000 many such coins independently, then this mu is very large. Mu is either 5,000 or 10,000, and hence the bad event that the number of heads that you see deviates significantly from the expectation, it just drops exponentially. This is the story. Okay. And there is the other direction, that this just bounds the event that there won't be too many heads. What of the event that there won't be too few heads? So, there is an analogous bound for that. I am just going to state it here. The bound is x less than 1 minus delta times mu, it is less than or equal to So, here you have a different constant, but again ignore the delta and 2 for the time being. It is again decreases exponentially with mu. Okay. The second part is called, this is Chernoff bound. This is used almost left and right in analysis of randomized algorithms. The next thing is called union bound that we will use. It is a fancy name for something that you probably learned in school. So, union bound just states that if you just have two events or many such events, I hope I do not have to prove this, right. You can see why this is true. You can just draw a Venn diagram of these two events and see that it is true. Okay. And the final concept is a term which is used often. It is called with high probability. So, when does an event holds with high probability? Okay, so in the context of graph problems, say n denotes the size of the input, the number of nodes. We will say that an event holds with high probability, event E holds with high probability if its probability of the event not occurring. So, the complement of E is at most 1 over n to the power c, where c is some constant, say. Okay. And now the point is, n, as I said, for in the context of graph problems, you can think of it as the number of nodes, or in the context of any problem that you are considering, you can think of n as being the size of the input or something. Okay. And note that, I mean, it's okay to say that it's number of nodes, right, because the number of edges will be n square. I mean, and here c is a constant, so you can just change the value of the constant. Okay. Now, in one sense, if an event holds with high probability, then means basically with high probability the event holds. But why do we say that it ought to be 1 over n to the power c? Why it is the case? It's because often we have to argue, make an argument of the following nature, that there are many events, say E k, that holds, each of these events holds with high probability. From this we need to infer that the union of these events, the intersection of these events also holds with high probability. Okay. So, from this we need to infer that the intersection of these events also holds, this thing also holds with high probability. Okay. Now, how are you going to infer that? We can just apply an union bound here, right. Suppose we just want to show this thing, sorry, let us just do this derivation. What is the complement of this event? The complement is the union, right? Union of the complements, right? Okay. Now we can apply union bound. Okay. And since each of these events holds with high probability, each of these terms is less than 1 over n to the power c. There are k such terms, k divided by n to the power c. Now, this is also going to be with high probability as long as, I am writing here, k is polynomially bounded by n. So, let us say k is n to the power lambda, okay, at most m to the power lambda. Then this term is going to be 1 over n to the power c minus lambda, right. So, the point is that as long as you choose this constant c to be sufficiently large, you just chose c to be appropriately large, then you are allowed to make the following claims, that I have identified these bad events E1 complement, E2 complement to Ek complement. Each of these bad events occur with very small probability, then with very small probability none of these bad events will occur. Okay. And this is the basic structure of an argument that you will find in probably hundreds of different randomized algorithms. Okay. Any question about this part? Let us just do a quick example then. Okay, then just one question. Just look at Chernoff bound. For us to infer that the good event, what is the good event here? That this sum x is close to its expectation. We want to argue that this good event occurs with high probability. Then asymptotically, what should be the value of mu? How large mu has to be, expectation has to be, so that we can infer this, that the good event occurs with high probability. Sorry? No, actually that is the answer, log n, right? Ignore the constants here. So, if mu is log n, then it is e to the power minus log n, and you get 1 over n here. Okay? Let us, and again here is an informal theorem statement. Whenever you need to prove concentration bound, just try to ensure that the sum of the expectation here is of the order of log n. As long as you can ensure that, you are guaranteed to get a high probability bound on the good event. Let us do a quick example. Okay. Suppose we have a set, this set consists of n elements. Okay. Now, I am saying look at this random experiment. Randomly color each element red or black with equal probability. Okay. So, you look at each element, pick an independent fair coin, toss it, and depending on the outcome either color it red or black. And now, I am just telling you x is any given subset of S such that the size of this subset is sufficiently large. Say the size of this subset is lambda to the power 2, no, what this is 3 over delta square let me do this thing 6. Okay. Now, x is any given subset. Now, I am asking you what is the probability that x has been partitioned evenly with respect to this error parameter delta, partitioned evenly by this red and black colors. So, if you just look at red this subset x, you will see roughly equal number of red elements and black elements. You can just look at this formula here, right? Oh, here it is also x. Let us just make it h. No, it is confusing. Okay. This is this set h, right? So, let x h be the number of red elements in H, then what is the probability that x h exceeds 1 plus delta times what does this say y h over 2, because if this set H was partitioned exactly evenly, then the number of red elements will be exactly H over 2. Now, we are asking what is the probability of the bad events, that the number of red elements exceeds 1 plus delta times H over 2. Can you see that? You can immediately apply Chernoff bound here, right, because just put an indicator random variable on each element, that will be 1 if it is red and 0 if it is black, and you have x h equal to the sum of those random variables. Mu is the expectation of h, mu x, and mu is exactly equal to h over 2 by linearity of expectation. And so, the probability that x h is greater than this quantity will be that, and this is e to the power minus delta square over 3 times what is mu? H is 6 over delta square times C log n. So, mu will be 3 over delta square times C log n, right. Mu is half of each. So, 3 over delta square times C log n. This thing cancels out, this thing becomes e to the power minus C log n, which is e to the power minus log n to the power c. This is equal to 1 over n to the power c. So, this thing holds with high probability. Then what is the moral of the story? Again, as long as the size of this subset is greater than C log n, you get high probability bound 1 over n to the power c. And now, here is the strength of this argument. Suppose as before we are given, what part can I erase? Okay, let me just erase this part. Suppose we are given some lambda, some constant lambda, okay, lambda is some constant. And suppose we tell you that there is a collection of such subsets H1, H2, H3 and so on. So, H1 till say Hk, where k is n to the power lambda. But you are not told what these subsets exactly are. You are just told that there is a family of n to the power lambda such subsets, and you just want to ensure that each of these subsets will be split evenly by this coloring. Okay? Then again, can you say how large each H has to be so that you can infer a high probability bound on that event? Anyone? So, the event you are considering is, the event is each Hi is split evenly. By the coloring. Sorry? Yes, some C log n, or suppose you want a high probability bound where the parameter is 1 over n to the power c, then you can see that each Hi has to be greater than some constant that will depend on delta first. Okay? I am just ignoring that part, this is just some constant, times c plus lambda log n. Can you see why? I mean, just redo this analysis here. Here it was c log n, this c was appearing here, you got log n to the power c. Now, I am just replacing this c by c plus lambda. So, here you will get log of n to the power c plus lambda. So, if each Hi is this much large, then you can just say that probability that Hi is not split evenly is at most 1 over n to the power c plus lambda. And there are at most n to the power lambda such events, such subsets. So, the bad event, that probability that some Hi where I belongs to 1 to k is not split evenly, that is going to be n to the power lambda by n to the power c plus lambda c. Okay. Now, what does this mean? Note that c and lambda, they are all constants, right. So, the thing is that basically this is O of log n, big O of log n. Okay. So, the moral of the story is, as long as you just restrict yourselves to sets that are of size at least O of log n, at least log n, ignoring the constants, then you can guarantee that if you are just given polynomially many subsets, each of those polynomially many subsets will be split evenly. Okay. And again, I just want to highlight this fact about this C log n business, okay, because the mu should be of the order of log n for this bound to become a high probability bound. Okay.
So, this high probability, the probability is over say graphs, so it's over the probability is over graph, all graphs of size n, exactly n.
No, the probability is over polynomially many different events.
So, when I say an event E is with high probability,
Mm-hmm.
so then I say that I do this probability over all graphs of size n.
No, let me just state it as follows. You are given a graph, the graph is fixed, the graph is deterministic. Now, you are running a randomized algorithm. So, the outcome of that random algorithm will be some random events, and you can associate various random events with that algorithm, right. And the graph is fixed. When I say that E is an event, I just mean it corresponds to some outcome of the randomized algorithm.
Coloring is not fixed, the graph is fixed.
Coloring was,
In this example, we are the randomization is because of the coloring.
yes. So, the set systems are fixed in this example. And if this is your worry of, I mean, if this is why you are confused, I mean, this example does not talk about graphs, right. I mean, here just it is a set of n elements. Okay. Okay. Any question? Then we are going to move on to the actual part. I mean, okay. So, let me just erase everything. Okay. Now, can you recall in the dynamic connectivity problem, what was the hard part? The hard part was you are maintaining a spanning forest and some tree in this spanning forest is getting split because a tree edge is getting deleted, and now you need to find a replacement edge. Okay. Now, suppose I tell you I am just going to give you an algorithm or a data structure that will just find you that replacement edge in worst case polylogarithmic time. Can you convince yourself that the problem will be solved, right? And this is what we are going to do. So, we are just going to design a data structure which just finds a replacement edge quickly in the worst case time, but it will be randomized and with high probability. So, with some tiny probability it might fail, okay? And you can detect that it had failed in the sense that it did not return you any tree replacement edge, but you cannot be sure that no such replacement edge exists. So, that is the probability of error. Okay. So, we are just going to define this cut set problem for the time being. Exactly. So, the algorithm will have the following guarantee: it returns you an edge, you can verify that that edge is a correct replacement edge. Otherwise, it just says no. There, with some tiny probability, it might have output a false negative. Okay. So, this is the cut set data structure. I am going to define this first. Okay. So, what is this problem? I am now just going to define a problem that might be interesting in itself. So, we have a node set of nodes, this is V and this is fixed. Now, we have two different edge sets. This is E edge set F. Now, we will consider this graph GE. And we will consider this graph GF. And we are guaranteed that GF is a forest always. This is a guarantee that is given to us. Okay. And finally, the interesting thing is E and F can be completely unrelated. So, earlier in the previous lectures, F was a subset of E, right, always. Right now, you just think of two different graphs, G of E and G of F. They are defined on the same node sets, but the edge sets are completely unrelated to each other, and you are just given the guarantee that GF is a forest. Okay. What are the updates? That you will support? Of course, you will support the insert. This means insert the edge UV to the forest, and this means that U and V belongs to the different components in the forest. Or you can insert UV to E. Here there is no restriction. Okay. And you have delete UV from F, you also have delete UV from E. Now, the query, this is the most interesting part. I am just going to call this thing cut edge. Okay. What does this do? Let TV be the tree containing V in F. Okay. And the cut set query just tells you, asks you this question: is there a replacement edge from E with respect to F? So, basically, is there an edge x y that belongs to E such that x belongs to this tree, but y does not belong to this tree. So, the picture is this is V and these are the forest edges F, and the tree edges can be anything, you do not know. I mean, you can see that there might this UV, this edge might be present in the forest and it might be present in the tree, you do not care. But when you are asking this cut edge query, it just looks at this tree and tells you if there is a cut edge with this edge belongs to E, this does not belongs to F, and it joins some other tree. And for the time being, you forget about the fact that you are then going to use this edge to join these two forests, okay, in the dynamic connectivity problem, because that will create some more subtlety and we are going to ignore that for the time being. Okay. But can you so the cut edge query will either return no, meaning there is no such cut edge, otherwise it will just return you explicitly one cut edge. Okay. And we are just going to design a data structure that answers this supports these updates in polylog n worst case time and supports this query in polylog n worst case time. This is the first half. Okay. Let me erase this part as well. Now, here is the main idea. The node set is fixed, right? So, you assign an ID, an identifier to each node, and this identifier will be a bit string consisting of log n bits. So, ID of a node x, we are just going to represent this as xb, is a zero one bit string and these IDs are unique. So, xb not equal to yb if x not equal to y. Now, one question, the length of this bit string, the definition is clear, right? xb is just a string of bits 0 and 1. And you see that the length of this bit string has to be at least log n, right? Because if you have log n bits, how many different combinations can you express? It is 2 to the power log n, right, which is n, which is v. So, for each node v you can find a distinct unique combination, and if there were less than log n bits you cannot represent all these nodes. Now, what do we want to do? Given these IDs, any edge will also get an ID. You can just concatenate the IDs of the two endpoints. So, each edge and okay, and these IDs are fixed in advance. The IDs are not changing dynamically because the node set is fixed. Okay. Now, when an edge is inserted, you can assign the following ID to this guy. So, each edge say UV as ID which is basically you just take the bit string for U, bit string for V, concatenate it in any arbitrary order. You can put U first or V first, does not matter. Okay. And then again, as you can see, if you are just given two different edges, you can just look at these two edge IDs and you will see that these two edge IDs are different, right. Okay. Now, this is a forest, this is the forest F, this is a node V, this is the tree containing V. We are just going to define this set C of V, we are just going to call this cut set of V. This is basically the edges in E that are going out of this tree, okay, somewhere else. So, this is the tree. So, this is the edges in E such that x is in TV, y is not in TV. This is the cut set. Okay. I am just going to do this definition and then we will see what is going on. We define this field value of V. What is the value of V? You just look at all the nodes in this TV . Sorry, I take it back. First, let us define the value of V as follows. Just look at all the edges in E whose one endpoint is V. So, these edges, some of them might be going out, some of them might be going in, okay, these edges. Take their IDs and then just sum them. This is a 0-1 sum. So, this is an XOR. Okay. And finally, if you are given a tree in this forest, this is TV, right. Value of a tree in this forest is simply you look at all the nodes in this tree, sum their values. So, this is an XOR sum, sorry. Okay. And suppose you are just maintaining these values. Oh yes, everything here is an XOR sum. So, okay. Now, why is this interesting? This is F. Suppose I give you a tree T. Okay. And suppose I ask you, is there an cut edge that is going out of T? And suppose, so this is a node V, right? This cut set corresponding to this tree. So, the cut set for each node V in this tree will be the same, right. There is exactly one edge in this cut set. So, there are many edges. So, the size of this cut set is 1, suppose it is the case. What does this mean? There might be many edges in E that are going between two nodes here. There might be many such dotted edges, right? These dotted edges are in E. But there is exactly one dotted edge that goes outside. Okay. Now the question, looking at this thing, value of t, can you retrieve that edge, that cut edge? There is exactly one such cut edge, okay? And let me just tell you, this is say x and this is y somewhere else.
So value t will give you that edge.
Exactly. Let us just pause for this moment. There is exactly one cut edge x of y, okay? If this is the case, then I claim that value of t will actually be the identifier for x and y. Let us just pause here for a couple of minutes. And can you figure it out yourself why it is going to be?
When I'm doing this x comma v, so you're doing at the x coordinate, you are doing XOR and you are doing at
Yes. Yes, so that is the point. So suppose here is okay, because you need to follow this, because if you do not follow this, then it will be lost for the rest of the talk. So suppose here is an edge x prime y prime that was in E. Look at where this x prime y prime is appearing in this sum. It is appearing twice in this sum, right? Once at x prime for x prime, once at y prime. And when you sum, do an XOR sum of this identifier, so it is appearing twice. This thing is appearing once at the y prime end, and you are just, it's appearing once more at the x prime end. And when you are summing them, you are XORing two bit strings which are identical. What will you get? You will get 0, right? So all the edges that are lying inside this tree, they are getting cancelled. And what is happening to this edge? This edge is appearing exactly once because it has endpoint x y, and so this edge will be retrieved. Okay? Any question? So if there were exactly one cut edge or no cut edge, then just by looking at value t, you can answer this query, right? How can you answer this query? How can you maintain these things? To answer this query, so I claim the first attempt at a data structure is you just maintain these values v at each node and at each tree, and when you are asked this query, just look at value of t and return it.
Value of t is 0, we may have no cut edge or we may have more than t.
Exactly. So for the time being, as long as we are given this guarantee that either there is 0 cut edge or there is 1 cut edge, this is a deterministic data structure that is going to answer this correctly, right? Now my question is, this is not the full answer, right? Even if there is at most 1 cut edge, even then we need to maintain these values. This is a data structure problem. I mean, this forest f is changing dynamically. This is getting added, deleted, these edges are getting changed dynamically in E as well. We need to maintain these values. So my question is, how are you going to maintain these values? Any data structure that comes to mind?
Whatever we try to do, whatever we were trying to do last time.
Sorry?
Whatever
Yes, exactly, that will work.
We use this.
Exactly, that will work. And the simplest thing is that any ET tree will work. So, if our just job is to maintain this forest f and these values, can't we just do an ET tree on this forest? So, ET tree where earlier if you recall, using ET tree we said that we could maintain the size of each of these trees, because we could just associate a counter with each node v that will denote its size. Instead of size, we can just maintain the values also using ET trees. You can just go back and check that it can be done, or using top trees. Okay. So, basically maintaining the value v's is very easy, right. If you are just asked to maintain this value v, what will you do? When an edge EUV is inserted, just add its bit string to the sum you already have. When an edge is deleted, just subtract it. Okay. So, maintaining the value v's is easy. How will you maintain the value t's? I mean, you can just look at this rooted tree, and at each node you can just maintain the value of the subtree, and you can then aggregate them when you are adjusting the ET trees. Okay. So, I am not going to go into the detail, but you can just treat it as an homework that you can just maintain these things using ET trees or top trees. Okay. Okay. So, let me just write these theorems. If our query was, I am not going to write it, so if our query was, we are given a node v, just look at the tree it belongs to in F, just return the value of T v. What we have discovered is, if we just forget about this query, we are not considering this. If we were to answer only this query, then we can do this in O of log n update time. Okay. Now, we are just going to assume this as a black box, I mean forget about this cottage query. Assume this as a black box, and using that we will just try to answer the cottage query. Okay. Now, how are we going to do this? The trouble is that, okay, let me just use this as a if there were only one edge, we were fine. If there were 0 edge, we were fine. The trouble is there might be many different cottages. So, suppose and they might go from different directions, and so suppose so CT is basically the cut set as we defined earlier. You recall that definition, right? CT is basically the set of edges such that x belongs to T, y does not belong to T. Okay. So, suppose I just tell you that the size of this cut set is k. Using a randomized algorithm, how can you ensure that you will be able to retrieve one cottage by looking at this value?
Sir, another very simple question. Suppose for now, I just want to answer the following query. Is there a cottage? I mean, is the set CT non-empty? That's all that I'm interested in.
even that you cannot do using this, because suppose it returns you 0, then you do not know whether this 0 is a garbage because there were many different cut edges and they all sum to 0, or it is a true 0 because there were no cut edge. Even that you cannot do. Okay. So, now I am just saying, if you just look at the things that we have described so far, can you see any idea as to if there are k cut edges? Suppose this k is given to you, I just tell you the number k. What will you do to retrieve one cut edge using these value fields? Let us just pause for 2 minutes. Yes.
Can we assume that all edges x u comma x comma y b, we have some order and x will come before y, like that is all edges going away from x have say x in the first half and the second half. There should be some protocol to design that, right?
Yes, you can.
Some ordering on the
Yes.
vertex and this.
Yes.
So then take every vertex and XOR that. If the value decreases, then there is a cut edge in there.
Okay, but the query time, the update query time is the size of the tree, right? Okay, the idea is actually very simple and elegant. It just says, okay, there are so many of these edges. If we had so right now we are storing these value fields with respect to the entire set of edges E, right. So, now suppose we discard some of these edge sets, take a smaller subset E prime and store the value fields with respect to the smaller subset, and in this smaller subset there is exactly one x y that is crossing this tree. Then by looking at this value field we can retrieve it, right. Now, I am just going to explain this thing in a different way. This k is given to you. So, suppose you say that select each edge with probability 1 over k put it into this set E prime, and then you just define value of a node V with respect to E prime, okay, as before. So, it is basically x phi in E prime the sum of this bit string, and again you just define value of a tree with respect to E prime. This is going to be okay. Then in expectation, how many edges will be causing this tree in E prime? 1, right, because there are k such edges, you have put each edge into E prime with probability 1 over k. Okay. And suppose you just get this expectation somehow, then just by looking at this value of t comma E prime, you can output that cross edge, right. So, what we have described so far is that this expected size of, if you just look at CT union intersection E prime, this is 1. This follows from linearity of expectation, right. Okay. But this is not sufficient, this just says that in expectation there will be one cross edge. We just want to say that with high probability there will be one cross edge. Okay. So, we need to argue that the probability this is 1, it is greater than or equal to something. We need to lower bound this probability for the time being. So, right now we cannot give any high probability bound, we will just say that this is greater than equal to 1 over c for some constant c greater than 1. Okay, so this is a basic probability exercise. How will you go about proving this?
If you are selecting each edge and putting it in E prime with probability 1 over k, then what is the insert and delete time for these edges?
No, insert and delete time for these edges is constant, right, because when this edge is inserted, you just sample it with probability 1 over k, put it into E prime, you are done. And when this edge is deleted, you just need to keep a pointer whether it was inserted into E prime or not.
So k is fixed.
For the time being, suppose k is fixed. Suppose we are just given this guarantee that the size of every cut set will be k. We will see how to do this, generalize this later on. Okay. For the time being, suppose we have uniform k. So, we just want to prove this lemma, and you can see that this lemma follows from basic probability. Why? What is the probability of this event actually? CT union U prime is 1. This event is, there are k edges in this set. You just first identify any one of them. So, this is k choose 1. Then that edge is picked with probability 1 over k, and the remaining edges are not picked with probability 1 minus 1 over k. This is exactly the probability, right? Any question? And now you see that okay, this thing is basically k, right? K choose 1 is k, and this k cancels out. So, you get 1 minus 1 over k to the power k what is happening here? I had something else, just one second. Yes, and you know that this term you actually do a better calculation. So, this is exactly equal to 1 minus 1 over k times k minus 1, right. So, you just say that this is greater than or equal to 1 minus 1 over k to the power k. Okay, you are just multiplying it once more, and this term is roughly equal to e to the power minus 1. This is a very common inequality that is used. 1 minus 1 over x to the power x is very close to e to the power minus 1. So, okay, the inequality that is used is 1 minus x is very close to e to the power minus x. It follows from the Taylor expression. I mean, you can just work it out which way the inequality is going. For any x, I mean, x can be positive or negative usually. I mean, okay, 1 plus x is very close to e to the power x, and so it is e to the power minus 1 over k to the power k, this is e to the power k. I mean, you can just Okay. So, this e to the power minus 1 does not matter. What matters is that with some constant probability we have the good event. Okay. But we want high probability. What will you do? So, this lemma we proved. I am going to leave out this calculation. So, what did we just say, that if we just sample each edge with probability 1 over k, then when we are looking at this cut set with constant probability, we will be able to retrieve one cut edge. But instead of this constant probability, we want high probability. What will we do? Anyone? Yes, right. Repeat this experiment log n times. So, basically you just keep e prime 1 oh, here I have C, okay. Okay, let me just do this thing D, DC, CD log n. Okay, I myself forget what the constant is, okay. So, then basically the thing is, for each edge E in E, and then say for each I from 1 to CD log n, do this. Sample E with probability 1 over k and put it into E prime I. Okay. And then if we do this, we have this guarantee, right, lemma, it follows from this lemma. Lemma 1, for each I we have probability of the bad event that this is not equal to 1. This is bounded by some constant 1 over lambda, where 1 over lambda is equal to 1 minus 1 over c. This follows from this, right. So, what is the probability that this bad event occurs at each of these subsets? This is CT union E prime of I not equal to 1 for all I. What is the probability? This probability is 1 minus, sorry, less than or equal to 1 minus 1 over c to the power CD log n. Again 1 minus 1 over c to the power c, this is roughly equal to e to the power minus 1 times d log n, and this is roughly equal to, yes. Okay. So, again this is just some tedious calculation, but just the thing is you had constant probability bound from one subset. To just get a high probability bound, it suffices to just repeat this experiment independently, order of log n times. Then what does this mean? Suppose we are again given the guarantee that the cut edges, the cut sets are of either size k or 0. Then we can just maintain this log n different subsets. And when we are asked this cut edge query, we can just go to each of these subsets E prime and ask what is the value. Okay. There will be one such subset with high probability which is correct, and looking at that we will be able to identify the edge. In the other subsets, what will we get? We will get some garbage.
So this property CT intersection E prime is 1. You're saying this is true for every tree in this forest?
This is true for if you are given the guarantee that the cut sets are either of size k or 0.
Given that guarantee for every tree in the forest?
Yes.
You're saying, so first of all you prove this for just one tree, right?
Yes, and then you can take a union bound over all the trees.
We will say that there will exist a tree for, there will exist a E prime for which this is exactly 1.
Yes.
But how will we identify that?
I am just going to answer your question. But before that, to answer your question, there are polynomially many trees in this forest, right? And if for each tree this holds with high probability, then for all of them it holds with high probability.
So essentially what you are doing is you compute E1 prime, E2 prime and so on. This is for all forests, all trees together. And then you
Yes.
say that for each tree one of these EI set is correct.
Yes. So, the way these E primes are constructed, we are not looking at the trees, right? I mean, we are just looking at the edge set. Okay.
Sir, I'm very confused. Completely confused with what's happening. So what you have and what is the process of finding these things? Because I'm completely confused with both of these things. What is my input and what is my output? I'm confused with both.
Okay. Right now, are you confused about the data structure that will be used to maintain this?
No. So I don't know what you have and what questions. So I have some tree which I was trying to maintain or something because I probably want to answer some question, right? And I really so I don't know how you're storing your objects such that this I get this point that I have my F and I have my E, right? And I'm maintaining my F in some way, right? And at some point of time, I get these questions about, hey, is there a cut edge from this, right? Now, to answer that question, people in the beginning we were trying to keep some vertices or like some kind of questions and queries we are trying to do. Now, at this stage, so from beginning are you maintaining something, or when some queries come, you are trying to do something starting with your E? I mean, that's
Okay. So, right now what we are saying is, we are maintaining these E primes first of all.
okay.
These E primes can be maintained in constant update time, or sorry, log n update time. Can you see? Yes.
Is these E primes in the beginning you have been given like these E primes also you are updating?
Dynamically.
Okay.
So, one question is, how do we maintain these E primes dynamically? That is the first question. How will you do that? An edge is inserted into E. You just go through this for loop, and
So let's keep two things here. Okay. There is a graph which has this V comma E, and let's call that I have some support objects. Okay. Let's call these support objects as E prime 1, E prime 2, E prime CD log, right? And I'm going to use these support objects to answer some of these queries.
Yes.
Is this what we have?
yes.
So actually we have number of 3 times these E primes.
No, these E primes are independent of the trees. right? If you just look at this for loop, how is E prime constructed? E prime is just a subset of E. You just look at every edge in E, pick it into E prime with probability 1 over k. E primes are independent of
You are saying that CT intersection E prime will be 1 with
for all, yes. Okay. So far there are two separate questions. One is about the performance guarantee, the other one is how we are maintaining these structures. How are we maintaining these structures? We can just write it down here. Let us just keep this lemma in mind. How do you maintain this? What are the updates? The updates to consider are that an edge is inserted into E. What you do? We will talk about this k later on. For the time being, we are assuming uniform k. This can be done, right? This is just one sampling. Just insert it. What is the time taken? Log n, of the order of log n. So this takes log n time. How will you delete an edge from E? When an edge is deleted from E, how will you update this E prime i's? You will just store a pointer for each edge u v, you just store a pointer to those u prime i's where it is part of, and just delete that edge from those E prime i's. It is not difficult, right? Can you see what I mean? This takes order of log n time again. Yes, even then it will be polylog n time. The thing is that you just need to find out if given an I, you need to find out in constant time whether this edge is part of E prime I or not. You cannot afford to go through the entire list of E prime i's.
Oh, it is. So we are maintaining this E prime as a list.
Yes. Okay. So the thing is that these E prime i's, they can be maintained. Now, let us just define one other thing. Called cut value data structure. I am just inventing this name. This is defined with respect to a node set, a forest, and an H set. What does cut value data structure do? It just everything is same as in here, it just answers this value query. It does not return the cut H query, it just answers this value query. Okay. The next thing is that you just maintain a cut value data structure for each E prime i's. So maintain one such data structure for data structure V f E prime I I ranges from 1 to CD log n. So, this can be done in polylog n time, right, because there are polylog n such data structures, log n such data structures, and we have argued earlier that this is just an ET tree. I mean, a cut value data structure is just an ET tree. Okay. And now, how to answer this cut edge query? Yes, that these data structures are enough. Yes. So, now I am going to deal with this k later on. Now, to answer your question, how to answer this cut edge query? Okay, so TV is the tree containing V. And this tree is the same in each of these data structures, right. So, you just visit these data structures one after another. And ask for the value of TV with respect to the H set E prime I. You collected CD log n different values. Now, what will you do? You just check that value is just a bit string, right. So, let us just say B is this is just a bit string, and this has two parts. I mean, say B1, B2. Let us just say B1I, B2I. So, this is the bit string you recovered from the ith data structure. This bit string has two parts. You just check if BI1 corresponds to a valid node in TV and BI2 corresponds to a valid node in V, but it is not part of TV. You can just check that, right. If you find that one of these two is not valid node, then what you infer? You infer that this is some garbage that you stored. And there will be many such garbages, because for many of these data structures, there will be multiple cross edges, and you are just XORing them all together and you do not know what you are getting. But what this lemma says is that there will be one I, with high probability there will be one I where we will get a correct value. So, you can just return that value. Yes.
Just like, so we need the guarantee. Okay, right now we need the guarantee that the number of cut edges out of any tree is either k or 0.
Yes.
So when you're doing insert or delete, it's not maintained. It's only maintained after a couple of steps, right? So right now assume that every cut edge is either 0 or k. Then you do an insert and one cut edge goes away.
Okay. Now, yes, to answer your question, I just need to consider the general case. What if this guarantee is not there, that k and 0 that we are just thinking of? Okay. What is not there? Because yes.
How do we know that there are not more than one cut edges, but they XOR, but they, I mean, when you are XORing them together, they give some valid bit string. So how do we know that this check will guarantee that there is only one cut edge?
We have the guarantee with high probability. There is some
There is some, but
contain just one.
Why do you care? You found the edge.
Yes.
Why do you care? Why you? So you
No, that edge may not exist. Right?
No, but
No, we are checking whether the edge
No,
is a
no, no.
valid edge. Then if it's not,
No, but other edges may XOR to give you the idea that okay, there is this edge, this edge.
No, you just check the existence of that edge, right.
you check whether that is actually.
you just check whether this is a valid edge or not, whether this is part of E. That you can check, right? Okay.
And if even for one of these the value is non-zero, then that means CT is not null. If CT was null, all of these will be zero, right?
Yes.
The error is kind of nice.
Yes.
You can actually work with.
Yes. But now the interesting question, how to get rid of this k? Because all these sampling probabilities, the way EI was constructed, EI prime was constructed, it depended on k, right? But this k can be anything, it can range from 0 to log n, 0 to n, whatever. How will you get rid of that? So, basically the size of this cut set can range anywhere between 0 to n. Oh, sorry, n squared, yes, it can range anywhere between 0 to n square. What we can do is, we just start from this interval from 1 and then discretize these intervals in powers of 2. So, this is 2 to the power 0, then you have 2, this is 2 to the power 1, this is 2 to the power j, and so on. So, how till 2 to the power L, where 2 to the power L is n square. Okay. So, L will be of the order of log n, it will be 2 log n actually, something log n square. Okay. Now, suppose you are interested in a cut set whose size is k, okay. K will lie somewhere in this interval for some j, right. So, what we have discussed so far is, if you had sampled each edge with probability 1 over k, then everything will work all right. You can just redo this analysis and say that if you had sampled each edge with probability 1 over 2 to the power j, then also it will be fine, because this is very close to being 1 over k, not too much of a difference. Okay? So, this gives you the idea that you maintain these sets E prime I j, where I ranges from, as before, 1 to CD log n, and j ranges from zero to log n square. Okay. And then how these sets will be constructed? If you just look at any edge E, you just have to check whether to insert this guy. Okay. Now, how many such sets are there? Subsets are there, E prime ij's. Again, polylog many such subsets are there, right? So, just as before, you could maintain these subsets dynamically in polylog update time. And then for each ij, you will just maintain a cut value data structure here, you just modify it. Okay, for all ij. This is what you are maintaining. And now, can you answer the query? I mean, the update time will definitely be polylog n, because all you are doing is just maintaining these data structures. There are polylog n many such data structures, each can be maintained in polylog n time, you are done. Answering a query, what will you do? So, you are asked this query, cut edge V. Just go through all of these. So, to answer this query, what do you do? To CD log n and then j from, just look at this bit string bij with respect to E prime ij. Now, how will the analysis go? The number of cut edges going out of TV, let us say it is k. So, let us say that the number of cut edges it is k, and let us say that k lies between okay. Then you can argue that with high probability, okay, let this be j prime, okay. With high probability, there exists an I prime such that this E prime of I prime j prime intersection the cut edges out of TV is 1. This just follows from this fact, right? Okay. So, with high probability there will be one such data structure that outputs the correct value, and you can identify that edge and report that edge. But if you see that all these data structures failed, there can be two cases. No, actually there is just one case. With high probability, you will be able to identify that correct I prime and you will find a valid edge. But on the other hand, suppose you failed, you can fail because of two reasons. Either you get a 0 value for each of these data structures, or you get non-zero values for each of these data structures. In either of these two cases, you cannot be sure that there does not exist an cut edge, because there might have existed some cut edges, but when you XOR them, they turned out to be some garbage or they turned out to be 0. You are not sure. So, there is one-sided error.
What do you do when there are non-zero edges, non-zero garbage values, but none of them are action values? So then the analysis becomes a little weird. You know that there are cut edges, but then you have to, how do you
Again, can you please repeat the question, please?
So I do the CD log n or L into CD log n things. I get non-zero values in each of the j's. So I know there are cut edges. For each of the j's, if there is some I which gives a non-zero.
Yes, I know that there is a cut edge.
But not all of the
are garbage.
Are garbage. Then
Yes.
what do I do? Then do I like deterministically do something? Or
No, no, no. Then you just report failure. So that's why it has one-sided error, but that will happen with very small probability.
So that I don't fail.
Yes. So in that case, you just report there is no cut edge.
But I actually know there is a cut edge, I just couldn't.
Yes. Okay. So the guarantee of the algorithm will be such that either it outputs you a cut edge, correct cut edge, or it says there is no cut edge. If there is no cut edge, it says, then with some tiny probability it might be outputting some wrong answer. That is it. Clear? Okay. So we will have to continue next class, but before that, before you leave, we basically have solved this cut set data structure in polylog and worst case update time with one-sided error. Do you think you can use this to solve the dynamic connectivity problem immediately? Okay, what I will do is I will just spend 10 more minutes to just trying to convince you that this actually does not solve the dynamic connectivity problem, and then we will continue the next class. Okay, so dynamic connectivity. In dynamic connectivity, this set F you are constructing yourself. This forest is not given to you, right? Only edges in E are being inserted or deleted. So what you can do is, you can maintain a dynamic forest, say, so here is dynamic connectivity, okay? Let me just try to convince you. So the input is just E, and what you are trying to do is you are maintaining some F that is a subset of E, that is a forest. Okay. Now suppose the query, the update is you delete some edge. Okay. So you just consider this update. And it so happened that you discovered that this UV was a forest edge. So here is U, here is V. You disconnected it. Then the natural thing will be to ask this cut edge query, right? Okay. You ask this cut edge query and you got some XY. What do you expect? You just insert XY into F and continue.
We should this Y be in this. We should delete XY from E.
Oh, okay, fine. No, delete XY.
So what I'm saying is that you have this F and then you have this E. So that F intersection E is empty. So your entire graph, right? Okay, so
Mhm.
the
We
entire
are
graph
not
is E
maintaining
union.
anything like that. Why should F intersection E be empty?
It doesn't say anything, right? E and F are unrelated, it just said.
Okay, I maintain the constraint that intersection is empty. And I'm trying to solve dynamic connectivity using this.
Okay, so you are just saying that
Whenever I pull out an edge from E, it goes into F and it's no longer present in E. So
Why?
the job of E is to only provide us with cut edges. That is the constraint I'm making.
yes, but okay, first of all, I do not see why you would want to do that, but even if you do that, there will be another problem. The
See, the reason I want to do that is because suppose you have inserted an edge into F, right? And later, so later when you try to sample another cut, get another cut edge, you might get the same E again, right? It could happen.
No, because the forest edges will always be internal edges with respect to the cut. So, it does not matter whether you are sampling them or not sampling them. Right? I mean, it does not matter whether you are sampling or not sampling the internal edges. You only care about the cross edges, and the cross edges will always be in E minus F by definition. Okay? So, you just say that insert x comma y into F and you then continue. Okay? This was the idea, right? Can you tell me what will be the problem?
Why be in this?
Sorry?
Why should y be in this tree? Oh, fine. Okay, sorry.
No, it is dynamic connectivity, right? I will just give you one hint and then I will just pause for 2 minutes. If it were a deterministic data structure, I claim, if this whole thing was a deterministic data structure, there would not have been any problem whatsoever. We could just continue. But this is a randomized data structure with one-sided error. That will create some massive problems later on.
So the thing is, suppose you delete a whole bunch of edges, right? And then you have brought in a whole bunch of cut edges and they become internal edges. Now for that particular tree, so all this thing happens inside a particular tree, right? This is a particular set of vertices. Now for that particular tree, the number of cut edges has gone from some large number to some small number. All the while, when we inserted those edges, we insert them with a particular probability somewhere.
No, but you have taken care of the entire range by discretizing the probabilities, right? That is not the issue. The issue is this. Let me just try to convince you what the issue is. It is actually very subtle. We said that it will answer correctly with respect to the query with high probability. What does this mean? It means if you make polynomially many queries with high probability, all of them will be correct. Okay? But these queries themselves cannot depend on the internal randomization of the algorithm. These queries will have to be selected independent of the internal randomization. Let me just try to convince you why this is important. Let us just look at this coloring business. So, we had a set, I am not going to write it down, but it is just from earlier example. Okay? Set S of n elements, you color into each element red or black randomly. Okay? And then of course, forget about polynomially many queries. Okay? What we claimed earlier was, say suppose there were just two subsets H1 and H2, both of size at least log n. Okay? Then okay, forget about even two subsets, let us just consider one subset. What we just claimed earlier, pick any subset H that is of size at least log n, then with high probability H will be split evenly. Okay? This is what we observed. Now, suppose I tell you this, n elements, roughly n over 2 of them are red, n over 2 of them are black by Chernoff bound. Just look at the black elements, make a subset H out of log n black elements and ask whether with high probability H will be split or not. This complete guarantee fails, right? Because with probability 1 H is not even. Did you follow this part?
Absolutely. No, I don't know.
Okay. What is this statement? The statement is, given any subset H of size log n, with high probability that subset is split evenly. Okay. Where can I say this? Okay. Lemma. Okay. Given any H such that the size of H is log n, with high probability H is split evenly, right. Now, suppose I say that this lemma is false. I just want to show you that this lemma is false.
You're saying H cannot choose H after the color.
Yes. So, my point is, suppose I just want to say that this, I can easily falsify this lemma. How will I falsify this lemma? Look at the black elements. Okay. Let H be a set of log n black elements. Take any arbitrary set of collection of log n black elements and let that be your H. Does this H satisfy this statement that with high probability H is split evenly? It does not. What went wrong? The underlying assumption in this statement is that you first pick H, then I am going to randomly color the elements. So, the way you are choosing H ought not to depend in any way in the random bits used to make this partition. Okay? Otherwise, this whole guarantee will vanish. Now, the thing is, if you are going to do this sort of thing, you are going to solve dynamic connectivity using this approach. One edge UV got deleted. You made this query cut edge. You got a replacement edge back and you inserted it into your forest. Note that in the forest structure that you are maintaining, then the forest F itself that you are maintaining, it is now dependent on the output of this query. This much is clear, right? So, if Ft be using this approach, okay, Ft be the forest at time step t. In this cut set data structure, this forest is being changed by some outside entity who is not aware of your randomization. But if you follow this approach, then this Ft is completely determined by the outputs of your previous queries. Okay? And this is exactly the same thing that is going on in here. Then you cannot apply this high probability argument anymore. Okay?
There's something missing. I still don't get your point. Because at least this is what you said before. No, I see what is happening, but there is something I'm not able to get your what is. So here you are saying that okay. So in the beginning you said take S set of n elements, randomly color each element red, blue with probability count, and then how did you select this H or X, whatever you call that point of time? How did you select this S?
The implicit assumption was that this H does not depend on the random outcome, the coloring. The age does not depend on the outcome of the coloring.
No, this is what I'm asking, right? So first you colored, there also you said that you were coloring each element of the universe red blue with probability half. Okay. Now, which X we are talking after that? Which H we are talking?
Okay, so let me just do it like this. I should have done it probably the other way. You are given a set S of n elements. You pick an H. Okay.
Yes.
But you do not tell me which H you have picked.
Exactly.
Okay.
Right. So then this is the process itself is different, right? I choose H from this universe with certain way of whichever side it is, right? So here what you are saying, you first pick a color, you first randomly this, and then I'm going to pick.
Yes.
So is that the difference?
Yes.
It's the difference of quantification.
Yes. So in the earlier thought experiment, the thing is you pick a subset H and then you keep it secret. You do not tell me which subset you have picked, but you are not allowed to change it later on. And then I am going to randomly color the elements and I am going to claim that with high probability your edge set is evenly split.
So which is basically same as saying that if, so these two experiments is that if I randomly color every element uniformly random with probability half, and now I create some sample of H of some particular size with the same probability, right? Then this object will satisfy the invariant of the back side
Yes.
of half with this. Here what, right? Here what you are trying to say is that okay, here this H is fixed because you chose that H of set of log in black element, right? Now what I'm saying that this is for with respect to a particular, this is with respect to particular H, we cannot argue anything, right? So suppose all we are trying to do is that we are trying to put a probability space on say log n sized elements of H, right? There also we are computing exactly that, right? That we are computing, so we have this probability space where each edge of log n size elements are there as an element, right? In this big case, right? Now we are trying to give some probability distribution over there, and we are getting a different probability distribution over here on the same what do you call it, universe where each element has size, like each set has size log n, right? And can you tell me what is happening with some, maybe it's an example or something that in your old thought experiment, the probability distribution on these objects are different than when I take in this.
No, because the object set is different in these two thought experiments. The subsets that you chose, no, I really do not get how we are trying to formalize this thought, but
so probability distribution, like ultimately we are getting a probability distribution
on the elements.
Subsets of size log, right? So let's my family be all subsets of size log.
The probability distribution remains exactly the same on that space in these two experiments.
Okay.
The only difference is that the probability distribution remains exactly the same. The only difference is that in the second thought experiment here, you are picking your H by looking at that probability distribution.
So can you say exactly where that kind of thing is happening here?
So the thing is,
So
here
the randomized structure we are looking for is that there is some inbuilt randomization, and whatever query that comes.
is independent of this inbuilt randomization.
Correct. So where is the dependence in the way you say? So you're
That's
saying
true.
that the XY you are adding is
Yes, it determines the forest, it changes the forest.
but the query is still independent. This query is
Yes,
not even random.
yes, yes. So, this guarantee will hold as long as this E and F, it is chosen by some adversary in advance. So, before you just start the algorithm, the adversary decides, okay, this is the sequence of updates in E, this is the sequence of updates in F, puts it down on a table, and he is not allowed to change that later on. Now, you do not know that updates, but the adversary cannot change it later on. Whereas, here what is happening is, the forest F that itself you are getting, it depends on the previous outputs of your previous queries, and that means the updates itself are dependent on your previous queries, right, because you have to change this forest. You have to call this insert XYV F.
So this is the part that confuses me. So the forest that you have, right? So if you fix a particular tree, the set of cut edges of the tree is determined by the set of vertices inside the tree.
Yes.
So that never changes in this process. Right? Even if you replace some edge by a different replacement edge, the connectivity structure does not change. The set of vertices which remain connected.
No, but it's assuming that you are getting a correct answer, say.
Suppose the wrong answer will come only when there is no answer.
So what happens if on the place of login, I choose 100 login?
Doesn't matter.
Doesn't matter, the same.
If you choose the set after the random experiment, the lemma is gone. Because you can just bias the set to make the lemma false.
So here can we say that if we suppose fix a coloring first, I mean we colored every element with probability half, red or black, and then out of all log n element subsets, we choose one uniformly at random, then will the lemma?
Yes, then it will hold.
So the main difference is that instead of uniformly at random, we cannot pick a subset,
Yes.
and then for every subset it will not be true, but if we pick uniformly at random a subset, then
Because again, here is the highlight. When you are picking that subset uniformly at random, what you are doing is independent of what the coloring was. You are not looking at the random bits used by the coloring algorithm. As long as you are not looking at the random bits used by the algorithm, it's fine. You can do whatever you like. You can do deterministic, you can do randomized, but you are not allowed to look at the random bits. Here, precisely that thing is happening. So, let me just add one more sentence. There are two different statements, right, that here you are seeing these dependencies, and the second thing is an exact example to show you that something will go horribly wrong. Unfortunately, I cannot show you that. I do not have that example with me. That was not given in the paper as well, but I hope to convince you that this is not going to be a correct proof because of this reason. That if you just say that, okay, I gave you an algorithm for dynamic connectivity by using this approach, then the proof is faulty. Yes, go ahead.
Fundamental doubt in time probability. I see two ways of organizing this. I have a universe n. Suppose I fix a set h of at least log n. Now, or take all the 2 power n colorations, possible colorings, and amongst this good event occurs with high probability. This is one setting. The other setting is take a fixed 2 power n coloring, one of the 2 power n colorings. Now, amongst all the n choose log n sets, the good event occurs in high probability. Which of these two is meant here? Is this something intrinsic to the problem, or do we have to specify this? I mean, these are totally different probability distributions altogether, right? The distribution space itself is different. Or is it the same? Am I missing?
Actually, can we take it offline? I mean, can we just conclude the class? I will just talk to you right now after the end of the class, because I do not want to keep others waiting. So, tomorrow we are just going to continue with this, and we are just going to give you the complete algorithm proof for this.